In this movie, we will see an example of how to do a one-way ANOVA test for differences of groups in JMP. Our setup is that we have samples from different populations, and we want to see if all these samples come from populations having the same mean or are the means different across these populations. So here we have K samples, and we are checking for the equality of means across these samples. And the setup is the JMP resource or example in JMP, where there are 5 different lots of materials, and the idea is to test the torque on samples drawn from these various lots. So each lot has 5 data points or 5 samples, and we are given the mean for each of these samples. And we have to construct an ANOVA test from this for equality of means. So this is the data that we have. We have 5 jars, each sample from each of the 5 populations. If we bring data in JMP, this is what we have. We have each lot captured by a letter. So we have lot A with 5 samples and so forth. And we will basically implement the test discussed in this example. So I will just resize these. To do a one-way ANOVA, we would click on Analyze, then we'll click on Fit Y by X. Here our response variable is the torque, so I'm going to move torque to my response variable, and then lot is my X factor. And now notice that in ANOVA, our independent variable has to be a factor, and our response variable has to be a continuous variable. So we want to make sure that the data is set up this way. If not, if suppose your lot was number 1, 2, 3, 4, and 5, you would have then converted that into a categorical variable or factor variable and then moved it into the dialog box. If we click OK. Here, again, JMP just gives us the minimal output, but we can click here in the little red arrow and then look for ANOVA. So now we get a rich array of statistics. So if we kind of look at the original table, the way we do ANOVA is we capture the sum of squared total, and then we look at the sum of squared factor, again given by this formula, and sum of squared errors. So to do all these computations, these are our individual values. We will find the group mean. We subtract each observation from its group mean. And then we also look at the overall mean of the entire population. So the first sum of squares is the group mean minus the population. So we'll have these same values for all samples. Then we also have the individual observation minus the overall mean. And we have the individual observation minus the group mean. Then we can construct the sum of squares. We get sum of squares factor as 42.25, sum of squared errors as 32.8, and then the total sum of squares is 78.05. The degrees of freedom are respectively our number of populations minus 1. So we have 4 for number of population. Our error is, again, our sample size minus the number of factors we have. And the sum of squared total is our sample size minus 1. And the f-test is constructed as the ratio of the sum of squared factor and the sum of squared error. So these numbers can easily be obtained from our table. In JMP, we see that our sum of squared total is 78.0. And again, the numbers that we got over here in this analysis, 78.05 and then 38.2. Again, our sum of squared errors is 32.7, and then our sum of squared factor is 42.25. And then our F ratio is 6.898, and our p-value for this is 0.0012. So this makes us conclude that we reject the null that these 5 lots are coming from, or samples coming from populations having the same mean. They are coming from different populations. Now, one drawback is that it does not let us compare individual samples with the population, or it doesn't even let us compare between two different samples. All we can tell is that these 5 samples that have come from different lots are not from the same population.